Hi, what I'm going to show to you today is the momentum experiment for ENGG2300. This is the apparatus. We have a tank with a pump and a reservoir of water. On top of the tank we have the apparatus, which I'll describe in a moment. We come around to the side is where the controls are located. We have an on-off buttons for the pump. We have a flow control valve to regulate the flow rate through the pump, from the pump, and we have an output which from a flow meter, inline flow meter, that's displayed as a red number. When we turn the pump on, water is going to come up this pipe, up through this nozzle, which has a diameter of exit diameter of 8 millimeters, and it will strike a target which is mounted on this apparatus on top. The way we use this apparatus is that we can change shapes by unscrewing the target and screwing a different target on. So in this experiment we have 3 targets. We have a flat plate, we have an inverted cone, and we have an inverted hemisphere. So to start the experiment we would choose a shape and we would screw the shape onto the bottom of this rod. So the first shape I'm attaching is a flat plate. So this apparatus is going to be used to measure the force of impact of the water jet onto the target. Now to do that, in a previous type experiment we ran in this course, instead of having this apparatus, we just had a flat plate with a rod through it, and we had a force measuring device on top, and it directly measured the vertical force pushing up on this rod. In this experiment we're using a slightly different method. What we're using is a rod with a plate on top supported by a spring. And what you'll notice is that this apparatus here has a self-weight, mg, and if I put it down there it's exerting a vertically downwards force of mg. The spring is now compressed to a point where it is exerting an equal and opposite force vertically upwards. So that system is in equilibrium. So what we do, we then attach this to the top of the apparatus. So when we turn the water flow on, the water is going to come out of this 8 millimeter diameter nozzle and strike the object, which is going to force the object upwards. What we're going to do is apply known masses to the top of the plate. They will tend to push downwards. They'll provide a force equal to the mass times the gravitational constant, mg, downwards, while the jet of water is applying a vertical force onto the plate. So we need to, in order to measure the force, what we need to do is to know where the equilibrium position of the spring in the apparatus sits. So we do that by adjusting this pointer until it lines up with a reference line on the plate, so I know where that is. So that system is in equilibrium. So if I turn the water on and it strikes the object and forces the object upwards, that system is no longer in equilibrium. It moves upwards. If I then, so imagine we applied 50 newtons of force. If I applied 50 newtons of force downwards, that would come back to equilibrium. So we've taken a system in equilibrium, applied an unknown additional force, and we're balancing that by an equal and opposite force, and we're measuring the force we're applying by calculating m times g. Each of these, we have different sized shapes, weights, so we can adjust depending on the force applied by the jet. Each of the weights have got a mass written on them. This, for example, is 50 grams. Okay, so we'll start the experiment. Okay. I'm going to begin this experiment by checking that I know where the equilibrium position is for the apparatus by checking that the pointer lines up with the reference line on the plate. I'm then going to switch on the pump. I'm going to begin the experiment by starting with the valve completely open. As you can see, there is a vertically upward force being applied to the object. I'm going to try to counterbalance that force with known weights. As you can see, the weights have started to balance the upward force of the jet of water, but we're not exactly back to the same position. So at this position, the spring is at a different extension, so it's applying some additional or less force than it was applying when we started. So we have to adjust the system so we're back to the same extension of the spring. Now, we can do that by adding smaller weights on top to push it down. So one or big one is pretty close. We can by adjusting the valve on the pump. So as you can see, I can adjust the amount of force applied by the jet. So I adjust the flow rate until I get an exact agreement between the force up and the force down, and I record the mass of weights that I've added to here, which allows me to calculate the ENGG force downwards, which at equilibrium is equal to the force of impact of the jet on the target. What we then have to do is in order to convert the flow of water into a force, we need to know the volumetric flow rate. And we get that off the flow meter, which outputs to this red number. So as you can see, the number is about 29.8 units. That number doesn't have a set of units. It is a number which is proportional to the flow rate. So on the blackboard, there are calibration curves for converting the red number into a volumetric flow rate. To do that, you need to know which tank we're using. We have three semi-identical tanks, and the outputs from the flow meters from each part is slightly different. So in this particular experiment, I'm using tank number 3. So in your, when you write this experiment up as a lab report, you will need to use the calibration curve corresponding to tank number 3. So having recorded the red number allows us to calculate a volumetric flow rate, which allows us to use a momentum equation to estimate the force exerted on the stationary object, and we're directly measuring that by the downward force applied by these masses on the top. and the aim of this experiment is to assess how accurately you can predict the force of impact from the momentum equation compared to a direct measurement using weights and unit forces. So having this one data point we're going to use, what we'll do again is take some weight off. That means that the downwards force is now is less than the upwards force, so that the plate and the weights have moved upwards. What I'll do now is reduce the flow rate of the valve until I come back to equilibrium. I now have a lesser force of impact from the jet because I've reduced the flow rate, and now that corresponds to the lower mass sitting on here. So again, now you would record the 50, 100, 150, 200, record the masses on here, record the number, the red number coming out of the flow meter, and that gives you another corresponding data point comparing the force of impact from the momentum equation as compared to the force of impact of the mass. You do that 4 times. Once you've done that, you switch the equipment off. You take off the weights. You detach the original shape that we were using, in this case the flat plate. I'm going to attach an inverted cup. Now what you'll notice is that each of these shapes are different, so they probably have a different weight. So each time we change the shape, we have to check that we know where the equilibrium position is for this apparatus, so because we go back to that when we take our measurement. So we need to adjust the pointer to make sure that it lines up with the reference mark on the plate. So now the system is in equilibrium, and as before, we're going to imbalance that system by applying a force, an upward vertical force, and we're going to balance that by an equal and opposite downward force. What you will notice when you do this is that the different shapes at the same flow rates will take more or less amount of weight to balance them. So implying that the force of impact on the different shapes is different at the same flow rate. So in order to apply that in the momentum equation, you need to consider the control volume around the inside of the shape. So when we had the flat plate, water was coming vertically upwards, and you would have seen from the video that it was exiting that region horizontally. So the important thing to remember, so what we're going to do is define a control volume around here. So we've got water entering the control volume in this direction, and we've got it leaving the control volume in that direction. The thing to remember is that force is a vector. So in order to assess what's happening here, we need to look at x, y, and z components of the velocity vectors. So we have a vertical, we'll call that positive y velocity into the control volume in the y direction, and we have no y momentum leaving the control volume, it's all leaving in the x direction. So here we're applying a balancing y force with weights on top. So we are only compensating for any vertical force of impact on the jet. As it turns out, because the three shapes are symmetrical, when the water hits the flat target, momentum, mass times velocity of the fluid leaving the control volume is equal on all sides in the x and z directions. So they cancel out. So the only forces trying to create a movement of these shapes, these symmetrical shapes, is in the vertical direction. So there are x and y momentums operating out of the control volume, but because of symmetry, anything that happens on one side of the object happens on the other side in the opposite direction, so they balance. So there is no net momentum leaving in the x or z directions. There is only mass or momentum leaving. We can only measure mass and we're looking at the change in momentum in the y direction only. So the important thing when you do the experiment is to consider the direction that the water leaves the control volume. Because in this case, there is y momentum enters the control volume, there is no y momentum that leaves the control volume. For the cup, we'll just do the cone. For the cone, the water comes up, strikes the target, deflects in that direction, so it still has a y component. So the cone is stopping, you're losing some of the y momentum when the water exits the control volume compared to the momentum entering the control volume. But so consequently, if we attach this to the end of the rod, we would find that we'd have to apply a lot of flow rate, which is a lot of flow rate, which is a lot of momentum into the control volume to get this to move up and to this to move up. More force than was required for the flat plate. The cup works. I'll show you the cup. When the cup runs, water enters the control volume in the vertical y direction and it leaves in the negative y direction. So the amount of force applied to the cup is approximately twice the amount of force applied to the flat plate at the same flow rate. Because there is a bigger rate of change of momentum, because momentum comes in a positive y direction and leaves and you've got more momentum leaving in the negative y direction. So if it came in at 1 metre per second and leaving at leaving at -1 metre per second, the change is 2 metres per second. So if it enters here at 1 metre per second and doesn't leave in the y direction, so the velocity out of 0 in the y direction, it only has a change of 1. So, in order to apply the momentum equation, we need to have the balance between the momentum into the control volume compared to the momentum out of the control volume. So, if you have any further questions regarding the experiment, you can email me at shaun.manning@newcastle.edu.au.
Go.
When you come to write your experiment up and go to Blackboard, as I've mentioned before, you'll find the calibration curves for the flow meter. That's the red numbers that we read over here. And recall that we're using tank number 3, so you need to use the calibration curve for tank number 3, which is relating the red number of the flow meter to the volumetric flow rate in cubic metres per second. You'll also get a table of data from this experiment expressed like this. So you've got a table for the flat plate, the cone and the inverted cup. In this column we have the mass, which is the mass applied on here, which is the force, which is a mass we're applying here in grams. And we have the red digital number that we read from the flow meter. What we're trying to do is compare the force from the mass downwards is balancing, and we know what that, we can calculate that, is using mg, and then we're going to compare that against the equal force upwards, which we're going to use this number to work out, to use the momentum equation to work out the force. To work out the force from these masses, we're going to use mg. So M is the mass in kilograms, but we've measured the masses in grams. So we need to convert 600 grams to kilograms, would be 0.6 kilograms times 9.81 metres per second squared, will give you the vertical force downwards of the weight. The red number, you need to convert that to a volumetric flow rate corresponding to that mass. So that'll give you a flow rate that was produced by the force applied by that mass. Then use the momentum equation, work out the force there, force you calculate for the momentum equation, and compare the two numbers to see how good the momentum equation is by simply measuring the volumetric flow rate, knowing the diameter of the jet, so we can work out the velocity of the water leaving the jet, use an equation to estimate the force applied on the stationary target, and we're comparing that against the direct measurement. If you have any questions about the experiment, you can email me on shaun.manning@newcastle.edu.au. The email should be on the course outline. Cheers.